So also from me or from us here, welcome to our webinar. Today topic is basics of dressing super abrasive wheels. Following our agenda for the next hour. First of all, a small introduction of our company, of Rigor, definition of dressing, why we have to dress, factors influencing profiling, factors influencing sharpening, exposing abrasive coatings, and lastly, effects on grinding performance. So we come to the company introduction. We are Rigor. We now in the third generation. Our CEO is Konstantin Rigor. We was founded in 1967 by Wolfgang Rigor, his granddad. We are 60 employees. Our headquarter and main production is in south of Germany, as Ed told you before, in Affalderbach. That's close to Stuttgart. And we have a second small plant in Romania. We are focused and specialized in the production of diamond and CBN grinding tools, especially grinding wheel. Our industry or our main fields, main focus are in tool manufacturing, like the most of you are, I guess. Also in machinery and plant engineering and contract manufacturing. We see us as a partner, a technology partner from our customers. So we offer trainings and workshops, something like that here. Or we also visit some of our customers to do the workshops directly there. And we offer some workshop over 2.5 days with several partners. And also part of our cooperation with our customers, we can offer application engineering and also a dressing service. But I guess that's not so interesting for the American customers. So we jump to the next page. How we grind in Rigor. We have an in-house research and development center and department. So in our own plant is a Volmer V-Grind 360S. And here we make tests of our own products and of our own developed bonding systems. So we can make some tests for our customers and we can test our own products as well. And also we have the opportunity to show or do some demos at our own company. Here, following a quick example, what we grind. It's nothing new for you, I guess. Here, for example, just a ball nose cutter, diameter 16. That's our old standard fluting wheel, scope grind RMP3. Now, brand new, developed in the last year, a new solution for fluting. As well for the flute, we have a scope grind finish to polish the flute at the end with a mirror shining surface quality. And also for the cup wheels, we have some solutions. That's our solid solution for clearance angles, ODs and stuff like that. Also for gashing, that's the Rocker A2. That's a hybrid bond. Also for the radius and face grinding, that's a good solution. And also for this geometry elements, we can use the scope grind finish for polishing these elements. So we come to the main topic for today, how we dress in our company. We have several opportunities and machines in our company. So we have several Geiger APs, that's a manufacturer for dressing machines from Germany. Real, strong steel tanks, conventional dressing machines. Also, we have Rolomatic Profile Smart, a CNC machine for dressing. And last but not least, we have the Mitsubishi MV1200R. So we have the possibility to dress via wire cutting. But today we focus in the conventional way of dressing.
Okay, hello and welcome from my side as well. Let's start with the actual topic. What is dressing? Dressing involves two work steps. The first one is profiling. The second one is the sharpening. This together calls dressing. During profiling, our goal is to change the geometry of the grinding wheel. We aim to establish the macro geometry and to improve radial runout and the axial runout. And we can balance a little bit the grinding wheels by profiling. In the sharpening step, the macro geometry remains unchanged. At this stage, the focus is only exclusively on creating the micro topography. We just want to generate the tips of the diamonds outside the bond. Let's take a look why we had to dress. The first is the process conditions and grinding wheel geometry does not match. Like we need another shape, we need our form of the grinding wheel, and you got it from your grinding wheel distributor as a wrong form. The concentricity and the flatness accuracy are insufficient, or we have an imbalance at the grinding wheel. We had changes at the grinding wheel surface, at the grinding wheel topography during the operation. We had a loss of form or a big wheel wear during the operation, or the grinding forces increase significant. Or redressed. The types of grinding wheel profiling. Here I show you the most common dressing methods is profiling by using carborundum or aluminum oxide grinding wheels. We can profile by using a diamond form roll, by using wire erosion, the EDM dressing, or with an electroplated form roll.
Yeah, now let's get into factors influencing profiling. First up, we've got the parameters. Are we dressing synchronous or asynchronous, clockwise or anti-clockwise dressing? What cutting speed, feed rate, or depth of cut we are adjusting. Next point is the in-feed strategy. Are we feeding in or outside the grinding layer? And another point is cooling system. Yeah, so we can switch to the last point of this page.
Yes.
The last point are the specification of the grinding and dressing wheel. As I said, if I use corundum or silicium carbide, what grit size, hardness, or bonding system are we going with?
A super-abrasive grinding wheel is composed of three fundamental elements: the base body, the bonding system, and the abrasive material like CBN or diamond. The selection in each case depends on factors such as the material to be machined and the specific grinding operation. The bond holds the abrasive grains as long as possible, but it must also wear so that new cutting edges are formed. The bonding system also influences how easy it is to dress the grinding wheel.
Yeah, now let's move on to comparison of the bonding systems. Here we look onto the different characteristics and mainly focusing on traceability. We as first resin bonds. Resin bonds have a high removal rate, good cutting ability, and provide mostly smooth, cool grinding, but come with high wear. Classic resin bonds mostly are soft with good cutting performance and easy to dress. On the other hand, we've got the metal bonds with high hardness, good dimensional and temperature stability, and great thermal conductivity. And yeah, that's why these bonds are typically used for profile grinding operation and for abrasive materials such as glass or ceramics. And the third, or lastly, we've got hybrid bonds, which combines the advantages of both. So we have smooth and cool grinding with good lifetime. One important thing to add here is that what's described here. Each bond type can also be influenced in its properties by additional parameters such as fillers, pore formers, pressing force, and pressing temperature. Each individual parameter affects the wear behavior and grinding performance of the grinding wheel. And yeah, that's why individual bonds can deviate from the characteristics listed before.
Here we have a designation of a typical dressing wheel that we use at Riga. It's the C120 J7V36 S63. We will go through it character by character. The letters A or C mean that aluminium oxide or carborundum is being used at the dressing wheel. The number 120 is the grain size from 60 very coarse to 400 and more for a very fine dressing wheel. The letter J is the hardness of the bond. Here we go from the letters A to Z, extreme soft to extremely hard. The next number describes the bond structure from 1 to 18, with 1 being very dense and 18 being very open. And the last letter and number describes the type of the bond and the maximum operation speed. On this page, we summarize which dressing wheel grid size best fits the grid size of our grinding wheel. As an example, if the grain size of my grinding wheel is D54, I use a dressing wheel with 120 mesh. An easy way to remember this is the finer the grinding wheel, the finer the dressing wheel should be, and the softer the bond, the softer the dressing wheel should be.
Also, the rotational direction affects the performance of profiling. By choosing a synchronous direction, the effective cutting force is significantly higher. And so we achieve, as you listed here, or you see here, sharp grinding wheel, a rougher workpiece surface, and low grinding forces. By turning around the rotational direction into asynchronous, we generate a smoother grinding wheel, a finer workpiece surface, and higher grinding forces. Another point are the parameters of the wheels. the chosen cutting speed, and also the selected RPM. We at Rigor, we always recommend paying attention just to the rotational speeds and suggest a speed ratio of 1:3. So the dressing wheel should always run 3 times faster than the grinding wheel. For example, when you choose 500 RPM for the grinding wheel, you have to choose or adjusting 1500 RPM for the dressing wheel. If this if this ratio can be achieved, because it's not possible from machine way or something like that, the diamond or CBN grinding wheel must always run significantly slower. And another point, to prevent the spindles from starting to swing up or vibrating, please don't choose even speeds.
By that, I'm sorry, Fritz, by that, I assume you mean don't choose an even multiple, right?
Yeah, of course, yeah.
So if it's 500 RPM on the grinding wheel, the dressing wheel should be 1600, not 1500.
Yeah, I don't know.
Right. Okay.
Later we noted down RPM from 500 and 1500, and we use something next to them like 499 and
Right.
1533 or something like that.
Yeah.
Okay, and what is about the cross feed and the in feed? The cross feed depends on different factors, such as the width of the grinding wheel and the geometry being dressed. For example, when dressing manually, a lower cross feed is used for radius to avoid creating facets. Typically, the cross feed rate is around 700 to 1000 millimeters per minute for straight areas and 400 to 700 millimeters for radius. The in-feed strategy shows that less wear and sharper grinding wheel edges are achieved when the in-feed is made within the grinding layer. If the in-feed is applied outside, chips can occur and the wheel can become convex. You see it here on the right side of the foil. The wider the grinding wheel, the stronger the effect. Important for that is different geometries may require different strategies.
In the following videos, there's some examples of the dressing process as we do it at Rigor. And here you can focus on the cooling, and here you see how we cool in an indirect way. Here you see the work of our CNC dressing machine from Rolomatic, the Profile Smart.
And on the CNC machine, you see also that the dressing wheel never leave the dressed wheel, the grinding wheel. We every time in touch with the grinding wheel.
Now I have a look on the manual, on the conventional Geiger machine. And here you see the cooling as well. So we don't go with full pressure in the dressing process. We do it also in an indirect way. The next one is the dressing video from our 5-axis tool grinding machine, the Volmer 360S. That's an example how you can dress properly on this CNC grinding machine.
Okay, let's take a look at the sharpening process. There are normally two types of sharpening. We can sharp manual or by machine. The advantages of machine sharpening are a constant force to the grinding wheel, a constant infeed to the grinding wheel, and this depends to a consistent result. The manual sharpening, on the other hand, is strongly influenced by the individual operator, the individual guy in the front of the machine. But no matter if the grinding wheel is sharpened by a machine or by hand, we had to look at what is important. The direction of rotation during grinding must correspond with the direction of rotation during the sharpening. The sharpening stone should be soaked in oil or emulsion to get by the sharpening process a slurry during sharpening. Once the final depth has reached, a short dwell time should be applied to allow the grinding slurry to take the effect. Here you see a bigger picture about the slurry. What I mean in this slurry is the diamond powder is a little bit of the bond, a little bit of the corundum or of the aluminium oxide, and this is a very important thing for sharpening. We also have two videos for the sharpening. The first one shows the manual sharpening, and here you see is just doing by hand with on each side with different forces in different directions and so on. Also with a little bit of coolant. And the second one is sharpened in our Fulmer machine, also with a little bit of coolant, every time indirect. And here you see also how the slurry is built in this way. Here you see the slurry a little bit. And then we come with the coolant to clean up the grinding wheel.
Yeah, another important topic is the next one, is exposing grinding wheel surfaces, which means to turning back the body material so the abrasive layer can be used again. On the following page, we see some negative examples. On the left side, the broken manually exposed one, and on the right side, this customer turned too deeply, so there was no contact area anymore, and so the grinding rim broke out. That brings us to the initial question: when should a grinding wheel surface be exposed? When the abrasive layer and the core body have reached the same height, like here in the picture, or the body material interferes the grinding path. So next question is, how should a grinding wheel surface be exposed? The most important thing is to use proper machine and tools, not by hand, ideally on a lathe with a suitable turning tool. And another important thing is, if this isn't done on the adapter, the wheel should be balanced again. Next question is, how much should a grinding wheel surface be exposed? In summary, as little as possible, of course, because sometimes the body additionally serves to provide support and absorb forces during the grinding process. But always please pay attention that the abrasive layer is never touched under any circumstances, because even small micro cracks on the rim or on the bonding can cause a damage and so a breakage of the layer of the rim from the grinding wheel.
See how our dressing process is affected. We carried out several tests that we would like to present you. We have done 4 tests. The first test is we have a correctly dressed grinding wheel with sharpening. The second test is we have a correctly dressed grinding wheel without the sharpening. Then we had an incorrect dress. We have used a much harder dressing wheel for this dressing process, but we have it sharpened. And the test 4 is incorrect dressed without sharpening. The procedure was always the same. We have only the dressing and the sharpening were different in these tests. We always used the same grinding wheel and ran the same parameters. The grinding wheel was a 1A1 with a diameter of 100 millimeters, a width of 10 millimeters, and a grit size of D54 in the RMP3 bond. We set a depth of 4.5 millimeters and ground with a feed rate of 100 millimeters per minute. Using these parameters, 5 grooves were ground into each carbide blank with a diameter of 12.
So we following the first trial, test 1, properly dressed, how it should be. So we use the machine you saw in the videos before, the machine from Rulomatic, the Profile Smart. We specified or choose the correct wheel, silicon carbide one, grit size 120, porosity and hardness J7, vitrified. So we choose the dressing wheel speed 1500 RPM. As I said before, we don't choose this even value, but just for notification reasons, we note it down like that. And we choose the grinding wheel speed of 500 RPM. We choose the cutting of depth per pass from 0.07 millimeters. The rotational direction we chose was synchronous. Our cooling you saw before was emulsion. Also, at the end, we sharpened here by hand with a corundum stone with a grit size 240. We choose the same speed of the grinding wheel. We choose 500 RPM. And because it was by hand, the cutting depth was approximately 5 millimeter. Here we choose both rotational directions, synchronous and asynchronous, to make it really sharp. At part 1, as you can see, the spindle load was very consistent, very moderate, and relatively low. The value was 28%, what is very, very good for some application on this machine. After 20 parts, we have still a very consistent spindle load, very moderate, but we increased 20% to 48%. After that, we took a look to the grinding wheel, and here, as you can see, we see some normal signs of use, no glazing of the bond, and no grain or edge chipping, no damaging. So everything is normal and in a good condition.
The second test was dressed like the first one, but without the sharpening process. At the first workpiece, we can see right away that we start almost 10% higher than the shaping condition. And we see a high peak at the first contact between the grinding wheel and the workpiece. After 20 workpieces, the spindle power increases by 27% to a total of 36%. The peak amplitude also was increased. When we inspected the grinding wheel after the test, we noticed the increasing signs of wear. There was slight load of the bond, but no grain or edge breakouts are visible.
So the next experiment was the third test, was dressed incorrectly and with the wrong wheel selection. Here we used same machine, same parameters, but different dressing wheel specification. Here we choose silicon carbide one with grit 180 and hardness and porosity with 0.9. And again, also hand sharpened as before in a proper way.
I'm sorry, Fritz, refresh my memory. Why is that the wrong dressing wheel?
That's just the wrong dressing wheel for the grinding wheel we used. It's not, we never can say.
No, I understand that. I'm sure some of my colleagues have my elderly memory here. I'm forgetting what the parameters of the wheel were that would make this an inappropriate dressing rule.
It was a hybrid bond with D54.
Okay.
And for this we did trials, and the proper one was the silicon carbide one with grid size 120 J7. And
Right.
now we did the same trial with grid size 180 and 0.9. And then we analyzed the
I'm with you.
spindle power and the influences to this process.
Yep.
And here you can see it at part 1. We started with a stable spindle load, but we started with 52%. Mm-hmm. But the graph you see is already uneven and not really consistent. And the real effect you see after 20 parts. After 20 parts, we have reached a high inconsistent spindle load of 88%. And especially when we hit the workpiece at the beginning, the spindle load rising extremely, and we reached a very high peak. And after that, in the following analysis, you see the wheel with moderate signs of use, but more than in the first trial, the bond is partially glazed, and distinct chatter marks from dressing are visible.
And the last test we have done was dressed like the third one, like the test before, but here also without the sharpening. I can say right from the start that we did not make the complete 20 work pieces because we already started at 64% of spindle load on the first workpiece. And on the second workpiece, the spindle load has already reached 92%. And during the third workpiece, the workpiece broke after the first groove. You see it at the picture on the right. When we here inspected the grinding wheel, we see that the grinding wheel showed strong wear. The bond at the wheel edge was fully loaded and glazed, and the clear edge chipping was visible. In addition, changes were seen in the outer area of the workpiece.
Yeah. So when we summarize this and when we then compare the spindle loads, we see clear differences between the results, and we see clearly the effects. So improper dressing can cause differences in spindle load of 40% or more. And yeah, even small differences can have a big impact in terms of the spindle load, the spindle life, the wheel life, or higher production volume.
And in this graph, we can see the edge and the diameter wear of the grinding wheels. And we see here the blue one is the diameter wear, and the yellow one is the edge wear of the grinding wheel. And you had to imagine on the first 3 tests, we already have done 20 work pieces, and on the last one, we just had done 2 work pieces. And you see how much diameter and edge wear we have after only 2 work pieces. The grinding edge increases by 80% only because of dressing and sharpening, and the diameter wear completely increased by 38% during the whole tests. This shows that proper dressing can greatly improve the wheel's lifetime.
So yeah, at the end, summarized here the most important points about dressing. The first point is to use a properly maintained dressing machine, no worn or loose spindles or axes.
Dressing grinding wheel matched to the grid size and the bond system.
And sharpening stones matched to the grid size and bond system.
We had to choose the correctly selected parameters like the cutting speed, the feed rate, or the depth of the cut.
And preferably cooled with oil or emulsion, not with full pressure. We should do it like you saw in the video in an indirect way, but it's important to cool with oil or emulsion. And at the end, we can repeat Marcus' words from the page before. Proper dressing can significantly extend the dressing interval, and workpiece quality and grinding performance are improved, while grinding wheel wear is reduced. And as a result, in the end, we significantly increase in productivity. And so we now try to fasten these things to keep the time. And now I pass to Ed again.
Yeah, thanks very much. Yeah, you covered a couple of key points really quickly. We've already got a couple of questions that I think are going to pull us back into some of it. You mentioned quickly balancing just a few moments ago. So how would you balance your wheels in general? Or what do you recommend?
We balance it with a balancing machine. We have a special balancing machine from, maybe you know the company Heimer from Germany.
Yeah, they're my competitor.
Oh,
I've said nothing.
then we
It's a
use
nice, it's a
another
nice
one.
machine.
We also have the NPM.
Oh, okay.
Maybe you know
That's
NPM?
better. That's a better answer.
Okay, we have both of them.
Now, as the final step in our production process, our wheels, every wheel who gets shipped to our customer are balanced on this balancing or special balancing machine.
Yeah, and you mentioned earlier how if you have to turn down the body, you would have to rebalance. I mean, I guess just broadly speaking, is that the only time you think it's necessary given the quality of your wheels, or would you go beyond that?
It's necessary to balance or to
You mentioned
retract.
you mentioned earlier if you have to turn down the body on the cup wheel, let's say, because the bond has now reached the level of the body, so now you have to turn it down. You mentioned that's a point at which you should balance.
Yeah, of course. When you don't do it directly on the adapter, then it's of course necessary.
Okay.
And also when you dress a lot of material and remove a lot of them, then you should balance also again.
Fair enough. Okay, one question that came in is this, and I'm not sure exactly what this refers to. I think one of the last examples. So if your silicon carbide grinding wheel was too hard for the hybrid bond wheel, I guess that was the example where you had your I think that was the second test, the third test. Basically, I think that's where I think
chosen.
Yeah, I think
we
he's
have
referring to the thing where I interrupt you.
Dressing wheel.
Yeah, right.
You
Right.
just had to find, normally we say to each customer, you had to find the right dressing wheel for your bonding system, which you want to dress, what you want to dress.
Right. And you had a
and because no customer can buy for each grinding wheel, for each binding system, a new grinding wheel. We had we say for us the hardness from H to J is okay for our bonding systems and so on.
Right.
We have a range where we can use for our bonding systems, but here we have looked for a harder one we never want to use for this bonding system.
Okay, and I guess I should say we have a link on our website to some rules of thumb about this, and I suppose because yours might differ. So actually, let's touch base after the webinar. Let me get yours as well up on the website. Here's an interesting question: why RPM versus surface feet per minute? Well, what we would call surface feet per minute, you would call wheel speed and the metric equivalent. Why revolutions per minute versus surface feet per minute for that 1-to-3 ratio?
It's depending on the diameter. If you have different diameters and you use the VC, the SFM, you have also other RPM.
Okay, so in your example, you're assuming you're assuming the same diameter wheel. Is that part of your assumption? I didn't catch that. In your 1-to-3 ratio, you're assuming the dressing wheel and the grinding wheel are the same diameter. Is that correct?
No, we use other diameters. Normally we start with a diameter of 300 for the grinding for the dressing wheel, and for the grinding wheels, normally the most our customer used are diameter 75 up to 150 for the tool grinding.
Okay, and so within that range. I'm sorry, go ahead.
Maybe if we start with a VC of 12 for the dressing wheel, and we go the ratio 1 to 3 down for the grinding wheel, and we have here maybe 4, meters per second, and we calculate with 100, with the diameter 100 and with the diameter 12, we got the same speed, and we have a ratio 1 to 1. 1 per 1. That's the reason why we use the RPM and not the VC.
Okay. Another question that came in: why is it important to have your sharpening stone soaked?
Because of the slurry we generate by sharpening.
To make the surface really sharp and open, it's important to have this. It's like a mat.
Maybe we can go back in the. Wait a second.
Maybe we can show the picture again, where we showed it. We make a mat with all the material together.
You see the picture?
Yep.
And because of that slurry, we need because of that, it's important that the sharpening stone is soaked. Because this in this slurry is diamond powder. There are the rest of the sharpening stone. There are rests of the bonding system.
So I take it. So otherwise, you would just be pushing the diamond back into the wheel, I guess, is what you're saying.
Yes. That's right.
And you push also the corundum into the pores of the bond system. So you glaze it a little bit.
Yeah.
And smooth the surface of the grinding wheel. And so with the soaked sharpening stick, you have a more sharpened, more open porosity of the bonding surface.
Right. Yeah. Okay.
It's to reset the binding system.
Okay. Well, okay, we used a little more than an hour with our glitch in the middle. I don't see another question coming in. Going once, going twice. Okay. Obviously, if anyone has anything afterward, reach out to me. In any format you like, give me a call or email and we can address other questions. And the last slide simply says, oh, I didn't include my last slide. Okay. Basically, we will have the archive up on our website in the resources section where we were advertising the live event. I want to thank everybody for coming. I want to particularly thank our two esteemed colleagues from Rieger. That was an excellent job. Little rush there for understandable reasons, but fantastic content.
Right, by video now.
I'm sorry?
We started the video again to say goodbye in a few minutes.
Okay. All right. Start your say goodbye video. Thanks, everybody.
Thank you very much. Bye.
Thank you.
And sorry for the issues with my internet.
Not a problem. Always a gremlin.
Maybe we see it at the grinding hub. Ed.
Yep. You'll see me briefly. I'll run through the booth.
Very nice. We have some beer for you.
Okay. Just a little one. Kleine.
Yep.
All right. Thanks, everybody. Bye-bye.